Welcome to Build Bytes Daily. Today, we're diving into an explainer that might just change the way you build web applications forever. Seriously. For years as web developers, we've had to make this massive architectural compromise when building highly interactive visual stuff. Think browser games, rich 3D product configurators, or heavy web apps like Figma. You always had to pick a path, and honestly, each path came with a severe penalty. But today, we're looking at a brand new, highly experimental browser capability that fixes all of that by literally bringing the DOM right into Canvas.
Real quick, here's our roadmap for today's explainer. First, we'll cover the DOM versus Canvas dilemma. Second, we'll meet the new HTML in Canvas API. Third, we'll walk through 3 steps to magic. Fourth, we'll check out some frameworks and stunning demos. And finally, we'll wrap up with limitations and next steps.
Section 1. The DOM versus Canvas dilemma. Let's start by painting the picture of this age-old developer struggle.
Think of the DOM kind of like a modern smart home. It's fully wired for accessibility right out of the box, text layout is completely effortless, and you get incredibly rich semantic features. Canvas, on the other hand, along with WebGL and WebGPU, well, it's like a beautiful, hyper-fast, off-the-grid cabin in the woods. It gives you raw, low-level access to push a grid of pixels for incredible 2D and 3D graphics, which is absolutely essential for fluid animations. But because it's completely off the grid, it lacks plumbing. It disconnects you entirely from native browser integrations. You lose accessibility trees, you lose native text selection, and you lose standard UI components.
So, until now, if you wanted responsive text or interactive form controls inside a 3D scene, you had to build these incredibly heavy custom workarounds. Just imagine wanting a simple login form inside your WebGL game. You literally have to code your own blinking cursor. You have to write all this complex math just to figure out text wrapping, selection highlighting, and focus states all from scratch, just to make an input box work inside that pixel grid. But what if there was a way to get the best of both worlds? What if you didn't have to choose it all?
Section 2. Meet HTML in Canvas. Google actually just introduced an incredible solution to this via a brand new experimental origin trial.
The HTML in Canvas API is basically the ultimate bridge. Going back to our analogy, it's like running power lines directly to that beautiful off-the-grid cabin, letting you leverage actual HTML and the DOM inside a high-performance pixel grid. You literally paint DOM elements directly into a canvas, or map them as a texture in WebGL and WebGPU. And the absolute best part? It stays fully alive. This isn't just taking a static screenshot of your UI. Because the HTML lives inside the canvas tag with an updated transform, the content remains totally interactive.
By letting the DOM handle your UI inside the canvas, you instantly get back massive features that used to be an absolute nightmare or literally impossible in WebGL. We're talking native copy and paste, right-click context menus, screen readers flawlessly reading your 3D user interfaces, and built-in browser translation right out of the box. Imagine hitting F12, inspecting a UI element inside your 3D scene with Chrome DevTools, tweaking a CSS background color, and watching it instantly update on a 3D billboard inside your game. Now that is a total game changer for developer experience.
Section 3. 3 steps to magic. Let's look at how we actually implement this in our codebases through 3 straightforward phases. We're going to walk through the high-level logic behind these 3 steps: setup, rendering, and updating the CSS transform. It might sound a little complex at first to sync standard web tech with a 3D graphics pipeline, but once you see the architecture of this API, it's beautifully straightforward.
Step 1 is setting up the canvas tag. You just add a simple attribute called layoutsubtree to your canvas. This crucially exposes any nested HTML elements to accessibility trees, so screen readers actually know they exist in the document. You also need to correctly size your canvas grid using a resize observer to match the device scale factor. Why? Well, because nobody wants to see crunchy, pixelated text on their brand new Retina display, right? Matching the scale factor prevents your beautifully rendered DOM text from looking blurry on high-res screens.
Step 2 is the actual rendering, which requires an explicit API call. For 2D, you use drawElementImage. For WebGL, it's textElementImage2D, and for WebGPU, it's copyElementImage to texture. You map this to an onPaint event. And guys, this is a massive performance win, because the paint event triggers only whenever the element redraws, like when you use your types in an input field or highlight some text. Instead of wasting resources re-rendering your UI texture on every single frame at 60 frames per second, it only updates the GPU when the DOM actually changes.
And that brings us to the final step, updating the CSS transform. Think of this just like painting a Google Maps marker.
You have to tell the browser exactly where this interactive HTML element physically sits on the screen relative to your 3D drawing. If you skip this spatial coordination, you end up with a completely broken experience where the user visually clicks a button in your 3D scene, but the browser clicks empty space 200 pixels to the left because it thinks the HTML element is somewhere else. Syncing the CSS transform keeps that interaction absolutely flawless.
Section 4. Frameworks and stunning demos. Let's see how this actually looks in the real world.
So calculating those 3D matrices into a 2D CSS space can be a massive headache. But popular web graphics frameworks are already making this incredibly easy to adopt. Frameworks like Three.js and PlayCanvas have already landed experimental support to do all that heavy lifting for you. In Three.js, for example, you just create a material and set the map using the new 3.html texture method, passing in your DOM element. Boom! It's mapped to your 3D mesh automatically. The API handles the syncing, and the relief for developers is huge. No complex math required on your end. The team at Chrome recently shared some jaw-dropping demos that show off things that were previously impossible without shipping megabytes of custom JavaScript. One stunning example is a 3D WebGL book where the pages are standard HTML. The text natively respects the browser's dark mode, and a user can literally right-click and translate the text perfectly into German using Chrome's built-in translation tools, right inside the flipping pages of a WebGL texture. Another demo shows a WebGPU jelly slider refracting light beautifully over a 3D model while still perfectly responding to a standard HTML input range slider.
Beyond just user interactions, this is a massive leap forward for discoverability and business value. Historically, a canvas was just a black box of dead pixels to Googlebot. If you built an entire interactive 3D portfolio, search engines couldn't read a single word of it. But now, because this API utilizes the actual DOM tree, web crawlers and AI agents can seamlessly extract and read out loud the text rendered inside your complex 3D environments, meaning your WebGL scenes are now fully indexable.
Section 5. Limitations and next steps. As with all bleeding-edge tech, we need to know the boundaries before going all in. The API has a few conscious limitations right now before you start rewriting your entire codebase. First, for vital privacy and security reasons, it completely blocks cross-origin iframe content from being drawn into the canvas. This is to prevent malicious clickjacking, where an attacker might draw your banking site into their 3D game to trick you into clicking something. Second, there are performance implications to keep in mind. Because the HTML in Canvas is drawn with JavaScript, scrolling and animations are tied to the main thread. Developers really need to profile the performance of scrolling content inside the canvas versus just scrolling the canvas element itself.
If you want to experiment with this today, the API is currently in an origin trial for Chrome versions 148 through 150. You can sign up for the trial for your site, or if you just want to test it locally, download Chrome Canary version 149 or above. Canary is meant for developers testing the bleeding edge, fitting perfectly for those of you who want to see the future of the web right now. Just flip the canvas-drawElement experimental flag to get started.
The potential to drastically reduce JavaScript bundle sizes by throwing out custom UI rendering logic in Canvas-heavy apps is absolutely huge. Not to mention the massive leap forward for accessibility and SEO in web games and 3D experiences. So, the big question is, what will you build with this newfound power? That wraps up our deep dive into the HTML and Canvas API. Like and subscribe to Build Bytes Daily for more web dev explainers. And please share your amazing Canvas creations with us down in the comments. Keep building, and we'll see you in the next explainer.